Also like to shout out to members of my team that helped with this. Glenn McLaughlin and Adam Wong have especially led a lot on this, and Terrence Lewis on the sysadmin team. I'll mention Yarda Fleeter's infrastructure through the talk. Wanted to sort of go over a relatively high level, sort of, what it is about the HTCondor ecosystem that I found to be critical to what we're doing at George Washington University. Our research computing team, research technology services, full service research computing organization, traditional HPC cluster, relatively modest scale, a little over 200 nodes, GPU, CPU, Slurm, InfiniBand, the kinds of things that you tend to see in campus HPC infrastructures. With the retirement of our original HPC cluster, Colonial 1, there were some nodes that we felt like still had some road time in them. And so we built a small teaching cluster, and we were able to start off on this pilot in HTCondor to do some more of the high throughput workloads that we tend to see. Also in the team we run the Internet 2 connector for the capital area, the Karen network. Of course, many of our researchers are interested in cloud resources, and so helping them engineer those solutions and data management using RedCap and Globus and so forth, and the usual cluster under the desk that they ask for assistance on and so forth, or all the kinds of things that we get involved in. George Washington University has several different schools, engineering, Columbia College of Arts and Sciences and so forth, and the support teams from those schools that had focused on research computing recently joined RTS in some restructuring of how we do research computing at GW. So we have a pretty broad set of talent and demands upon the team. This was to be a picture of our new Pegasus cluster. Colonial 1 is a little more photogenic at this time, so we have a legacy photo of that, but coming soon we'll get another Pegasus in here, but you can see the Battlestar Galactica theme of our systems. But we felt like, with the other problem, good news and bad news is Pegasus is a very popular HPC resource, and now we're seeing utilization often well into the 80s and sometimes 90%, which is great for utilization and see how efficient we are. And then users find that they sometimes have to wait much longer than they would have thought. With that said, like in many HPC environments, a lot of the jobs are really, single node run under an hour. Of course, there's jobs that run for up to 2 weeks is our limit on times. That's our policy. And also what was kind of surprising to us, we looked at the memory utilization, and we're seeing a lot of jobs that are using less than 10 gigabytes of RAM. So actually we have a fair number of high throughput type jobs on the cluster. But everything is Pareto distributed. There's long tails out there, of course, and these are sort of where most of the data, but what's the average is much higher. But a lot of things that we do here, a lot of the research that's done at George Washington, like again, many research universities fit nicely into high throughput computing and the scalability that provides us. So we have some of the nodes that were from the expansion of Colonial 1 from a few years ago that sort of became our initial foray into HTCondor, and worked a lot with the folks at the Open Science Grid and HTCondor team to get that up and running, and that became popular and people wanted to use that. So we wanted to expand that. We had a particular project come along that needed more storage capability than we had, and additional CPU requirements. So we had a pretty interesting OpenStack deployment that had been used for some cyber range applications and other very flexible things that Yarda Fleeter had done for us, and interesting infrastructure that lives actually in our Karen facility out at Equinix. And so we've repurposed some of that and been able to apply it as a sort of using that grid model to add to our HTCondor deployment. We're also in the process of bringing some GPUs from Pegasus over to our HTCondor environment. Logged in nodes don't necessarily need the GPUs, so we'll have some GPUs available in login nodes for testing and so forth. We felt like since we have them there, let's repurpose them into HTCondor. So a few things, we're at the point where we're starting to look at the next generation of growing that infrastructure somewhat and really taking advantage of that grid infrastructure. I'm sure some of you are saying, a petabyte of cluster. Well, that's interesting. That's a little different. A little science project we had going on. We thought, well, we've got it here. Let's give it a go. So looking forward to that. We actually, Yarda has, being an OpenStack guy, done a lot of work with Ceph, and so we've got a petabyte of Ceph and a petabyte of Gluster using as a comparison environment. But that's going to be a lot of interesting work going on there. But again, that was really to solve a particular application that I'll get to in a few minutes, where they had some more storage requirements. But what we're seeing is that sort of eclectic mix of high throughput applications that have come to us. And so we've just wanted to talk about a couple of different science drivers that have really been success stories for us. One of those, a genomics application using the 10x genomics platform to do some single cell RNA sequencing. Pretty interesting application here. Again, the issue here is lots of reads, lots of big pipeline to go through, and getting that pipeline to interact with the DAGMAN tool. So the Cell Ranger tool does sort of FASTQ counts and aggregations, the usual kind of things you see in these bioinformatics pipelines. In this case, in the single cell RNA sequencing application. We're ultimately looking at a single file with a billion sequencing reads. So this is going to take a lot of computational resources, but again, it breaks apart very nicely into numerous independent processes, not prices. I suppose I could make it independent prices too, but processes. And so we felt like that was a really good candidate for one of these high throughput constructions. And it's worked out very well, and they've been really happy with the results that they've been getting from that. Similarly, we had a physics application come to us. And this one, we especially worked closely with our friends at Open Science Grid, dealing with a big instrument down at JLab, where because of the expense of doing work on the physical machine, the simulations are a real important element for identifying what do you really want to go into this machine that can cost tens of thousands of dollars an hour to run. And so the Géant 4 Monte Carlo simulation environment was being used to work with this application. And here in this case, the researcher, graduate student working towards conclusion, needed to get results in a few months. And by the way, would need a few million core hours to complete that. So we went to the Open Science Grid community, and they were able to give us a hand getting this research done. This also, it was really nice to be able to work in a singularity environment, and that was obviously very useful for being deployed into the environment, making that very portable. And again, a great success story for being able to get science done, which is what we're about here. So our newest application is working again to do some sequencing. Now we're looking at the Konzo disease in Congo, which is a sort of metabolic and microbiota analysis that they're doing across different towns and cities in the Congo, and with our Children's National Hospital colleagues across town. So lots of data in a public health context, big collaboration between these institutes. And in this case, they want to gather sequencing data from, hopefully 1,000 individuals to do reference genomes and look at what is it that makes people able to be resistant to this disease or not. A lot of that comes from the microbiota as well. And this was going to be looking at 25 terabytes of data this year, and then looking to grow to 100 terabytes over the next couple of years. Again, the bioinformatics pipelines are very good at being adapted to the high throughput analysis that we have here. It's kinds of things that we're seeing in a lot of these pipelines. So that was another good example of the collaborations that we've been seeing to be successful at doing science. And that's really been the character of what's been strategic about using HTCondor and serving the high throughput workflows has also been those collaborations in the community and the developing a possible alternative resource to our big HPC cluster on the one hand, and relieving some of the pressure on the small jobs in that environment, but also building the relationships across our researchers and within the HTCondor and OSG community. And it's one of the things that's been most remarkable from my perspective has been, how useful the community has been and how helpful the community has been to get this going. So it's just been a really good experience for us. And, HPC clusters obviously can be adapted to these high throughput community applications. And so that will continue to be an important platform for us. But this has been a real strong effort for us. So it looks like I'm out of slides. So I thought I had a thanks slide for TJ at HTCondor Group. It's been especially helpful to us, and really appreciate the support from the community. So I'll give you back a few minutes of your time, I think.